Recently in the scientific computing department, the computational mathematics group have developed an algorithm that is capable of solving non-linear least square problems. Now let's talk about why this is an important development in the context of model design. Mathematical models are used to solve a whole host of problems, from being able to better predict changes in the economy to the design of new drugs to fight diseases. In each case, complex numerical models are designed to fit real-world observations. These models affect us all across our daily lives, so they must be designed accurately. Models are used to represent, understand, and simulate data that has been collected in an objective manner. When designed well, models allow us to form predictions and make logical decisions about the best course of action to take according to the data. Now, model design begins with a problem. The first step to designing a successful model is to understand what the fundamental nature of the problem is. And once this has been determined, we can use our current understanding of the situation to theorise a model that fits these defined first principles. Then, we must define the parameters of the model and collect appropriate data to solve them. Here, it is important to establish if a relationship exists between the variables by finding the regression line with minimal error. This is more commonly known as the line of best fit. And least squares allows us to prove if there is an existing relationship. If a relationship is found, it can either be linear or non-linear. And the difference between the two types of models is that the parameters of a linear model can be estimated in a linear manner, whilst the non-linear models cannot. Now, to visualise how regression fitting works, imagine you have collected your data and plotted it on a graph. On this graph, you then draw a line through the mean of y. This line is the average result for your dependent variable, and then you fix this line in place. Then, you attach springs to the individual data points and the line you have drawn. You notice that some springs are more extended than others. Now, if you allowed that line to move, the springs would exert a force on the line, rotating or bending it and shortening the length of the springs. By shortening the springs, we have found the regression line that has the least amount of error between our real-world observations and the model we have designed. In essence, the shorter the springs, the less error there is, and the better the model. Now, most models have a huge number of parameters to consider. Mathematicians consider a model fitting problem to be small to medium in size if it includes up to the thousands of parameters. In such cases, attempts at drawing a graph from a regression line would be futile. This is made even more challenging when the relationship between the parameters is nonlinear in nature. So, to solve this issue, we use algorithms and software to determine the regression line for us. And this allows us to design better models and make more informed decisions.